Welcome to This Explainer. Today, we're stepping right into our virtual classroom to unpack the ultimate blueprints of the universe itself, atoms. We're going to look at how we first learned to visualize them, why that classic picture is, well, kind of an illusion, and how modern scientists are essentially playing cosmic alchemists to forge elements that literally don't even exist in nature. All right, let's just dive right into this. I want you to picture a classic atom. Think back to your very first science class. The image that pops into your head is probably a miniature version of our own solar system, right? You've got this sun in the middle and little planets sipping around it in neat little circles. But here's the big question. Is an atom really just a tiny solar system? So here is our roadmap for today. 1. The atomic solar system. 2. Where the analogy breaks down. 3. Synthesizing brand new elements. And 4. The methods of nuclear synthesis. Let's kick things off with Section 1, the atomic solar system, visualizing the microscopic. This miniature solar system model is actually incredibly helpful for our brains to just grasp the basics. Much like the sun in our actual solar system, there's a dense, heavy nucleus right smack in the center, and orbiting around that nucleus are the electrons, revolving around like planets in a neat little cosmic dance. This solar system idea is just a fantastic conceptual tool. It establishes the ground rules, right? You have a center mass, and you have particles arranged around it. It gives us a really comfortable starting point to visualize things before things get weird. Which brings us to Section 2, where the analogy breaks, quantum contradictions. Okay, first up, let's look at the movement. In a solar system, planets follow predictable, fixed orbits. Like, we know exactly where Jupiter is going to be next Tuesday. But in the atomic world, electrons are a bit more rebellious. They don't follow fixed paths at all. Instead, they exist in these clouds of probability, meaning they're kind of everywhere and nowhere all at once, at least until you actually look for them. Second, the very glue holding the systems together is totally different. Our solar system relies strictly on gravity to keep those planets tethered. But down at the atomic scale, gravity doesn't even enter the chat. Instead, atoms are held together by electromagnetic and strong nuclear forces. Finally, and I think this brilliantly illustrates just how bizarre the quantum world is, let's talk about energy levels. Electrons in an atom can actually jump between discrete energy levels by emitting or absorbing energy. Imagine if Earth just instantaneously blinked out of existence and reappeared in Mars's orbit just because it absorbed a burst of energy. No way that happens in our solar system, but it is absolutely a fundamental rule for atoms.
Moving right along to Section 3, synthesizing brand new elements, cosmic mechanics in the lab.
So scientists don't just sit back and passively observe these atoms. They actively synthesize them. And by synthesize, we mean manipulating atomic nuclei in a lab to forge entirely new elements that don't exist naturally. We are literally talking about playing cosmic mechanic here, creating materials for cutting-edge medicine, nuclear power, and totally pushing the boundaries of the periodic table. And that leads us to our final section, Section 4, methods of nuclear synthesis: fusion, fission, and bombardment. To forge these brand new atomic realities, scientists basically rely on 3 primary methods of nuclear synthesis, and those are nuclear fusion, nuclear fission, and particle bombardment. We can actually break these complex actions down into 3 distinct choices. You're either combining nuclei together in fusion, splitting heavy nuclei apart in fission, or directing high-energy particles at a target in bombardment. It's kind of like a microscopic puzzle. Now, depending on the method you choose, the real-world applications are vastly different. Both fusion and fission are absolute powerhouse reactions used to generate massive amounts of energy, whereas particle bombardment is more of a precise tool. It's what scientists use to induce nuclear reactions and discover brand new elements. Let's look at each one just a bit closer. Okay, so with nuclear fusion, we are essentially slamming lighter atomic nuclei together under extremely intense conditions. By taking isotopes of hydrogen, like deuterium and tritium, and forcing them to combine, you build a heavier element like helium. And the crazy part? In the process, a neutron is released along with a truly staggering amount of energy. Conversely, nuclear fission is all about breaking things down. You take a heavy, unstable nucleus and hit it with a neutron, basically forcing it to split apart. It breaks into lighter elements and releases a vast amount of energy, plus some extra neutrons. And those extra neutrons, well, they fly off to split other nuclei, creating this massive, cascading chain reaction.
And finally, we have particle bombardment. Here, scientists act almost like microscopic snipers, directing high-energy particles straight at stable target atoms. The nucleus is forced to absorb the particle, inducing a reaction that transforms it into a completely new, often radioactive atom. I mean, this is literally modern-day alchemy right in front of us.
So we started today with a simple solar system drawing, realized the universe actually operates on bizarre probability-driven quantum rules, and learned that scientists are actively using those rules to forge elements that don't even naturally exist. I want to leave you with this thought. If human ingenuity can manipulate the very fabric of atoms to create the impossible, what limits of the universe are we going to overcome tomorrow? Thanks for learning with me today.